Hey everybody, we have the last topic of gigantic importance in chapter 1, and that is orthogonal circles and the inversion of a point across a circle. These two things go together, and they are the key to chapter 2. So they get a big fuss at the end of chapter 1. So let's do two things. I'm going to try and go nice and slow, so those of you who are Sketchpad rookies can try and pick up a little bit more Sketchpad experience. Remember, you have free access to Geometry Sketchpad on campus at Aquinas. Any library computer, math department, we got a few computers that do it, and then the computer rooms up on the 3rd floor of AB, they all have Sketchpad under academic software. You go academic software, mathematics, there's Sketchpad. So here's Sketchpad. I've made myself a circle. Let me show you one thing. You can tell when circles are not orthogonal very quick. If I have a center inside, I can't get a right angle here. This is where I'm trying to get a right angle. And if the center of this circle is inside, I have no chance. Anywhere in here, make it bigger or smaller. I can't make those circles orthogonal. But with the center outside the circle, I got a shot. So orthogonal circles, see, now look, I didn't construct it, but that looks a lot more like a plus sign right there. So you can eyeball your own construction. Like, for instance, that's no good. Does that look like a plus sign right there? You know, that's not it. That's not orthogonal. Orthogonal is somewhere around in there. And the circles can be really big. And if they are, you're still looking for that plus sign. You know, looking for a plus sign to occur, maybe right around here. That might be good. The size of the circle doesn't matter, but the center has to be outside. Okay, let's get rid of this thing, and we're going to actually construct orthogonal circles. One easy way, and this is really nice. If you can get away with this, this is so great. Check this out. I'm going to make a radius. I'm going to select the endpoint that's on the circle. I'm going to construct the perpendicular. And now I can put the point of another circle anywhere on here. And I get orthogonal circles. These two green circles are orthogonal, and the two blue straight lines are the reason why. Because I've got right angles. The radius is perpendicular to the tangent. The radius is perpendicular to the tangent. So this is what happens with orthogonal circles. One circle's radius is the other circle's tangent. That's what has to happen for orthogonal circles. So that gives you a quick way to build orthogonal circles. Isn't this great? Unfortunately, it doesn't help you for the general case where you have a very specific location where you need orthogonal circles. But while we're here, let's do a couple of things to demonstrate some of the facts about orthogonal circles. Since I have orthogonal circles in the picture, observe the following. I'm going to make a ray from the center of the big circle, and we're going to call that big circle circle O. So this will be the circle of inversion. Hang on, I can do this. And I want that thing to be bigger so you can see it better. So I'm going to increase text size. And increase size is Alt greater, or you can just go up here. While that point is selected, I can increase the text size. So you see that O getting a little bit bigger. That's good. Now, any ray from O to a point on this circle that is orthogonal to circle O, construct that ray and check it out. This point, right, I'm going to hide this other line. I don't need it anymore. Display hide perpendicular. Now here is a point and its inverse across circle O. So this is point B. This will be point C. B and C are inverses. And here's what it means for B and C to be inverses. Here's what it means. Measure this length. Oh, I need that distance. Oh, I got too many things selected. There's 3 points selected. Measure this distance from O to B. Measure this distance from O to C. I'm going to multiply them and show that it's the same as the length of that radius. So here's a radius squared. When that radius is squared, so I'm going to do the calculation right here. Go to number, calculate. You don't have to do this, but it's nice to be able to see what's going on. I'm going to do this number squared. So it's that number to the second power, and hit OK. 12.41 is my target. I'm going to multiply these two numbers. Now look, 2.21 times 5.61, it could be 12 point something. Let's see the actual calculation. And I'm going to get, I have a calculator screen open. I click on this, and it appears in the screen. Come on. I clicked on it. Come on, you. Why is it not appearing? It's got to appear inside of here. Don't give me these kind of hassles. Number. Calculate. There it is. Times this guy. And there it is, 12.4062. But when they put it on the screen, it's going to round to the 12.41 there. And check it out. I move the point B around, and nothing is changing except for these two numbers. Let me put them all on the screen here. OB and OC are changing size, but the length of the radius isn't changing, of course. And the product of OB times OC is straight out, never changing, 12.41. Now, I'm also going to change the size of this circle because I moved that point myself. I changed the size of the circle, and the 12.41 didn't change because I didn't change the radius of the big circle. I didn't change the radius of circle O. But OB and OC still multiply to give me 12.41. Isn't that cool? Now, to change all the numbers, I'm going to change the size of this circle. The big circle changes. Now, OB and OC have changed in size, but now 15.94 won't change as I move point B around. 15.94 stays constant. So that's what it means to have a point and its inverse. They have this very interesting relationship. There are entire chapters in some geometry books about points and inverses. We're not going to be doing those. We're going to focus on orthogonal circles and points and their inverses as preparation for hyperbolic geometry. But you could do an entire chapter on just what happens with orthogonal circles and points and their inverses as Euclidean geometry subjects, but we're not going to worry about it. All right, now let's do the last and most important. This is a must-know case. Let's say you have a circle, and you would like to get a circle orthogonal to this one through a certain point. You would like to have a circle, let's just do the inverse of this point. So let's call this point here, let's call it whatever they give us, E. And then this guy here, I want that to be O, because that's my center. It's a nice thing to always call your center O, because then in the picture, when somebody sees O, they know that, oh, that must be the center. Okay, so here's the construction to get the inverse of E. You do the ray through E, construct ray. Then you do the perpendicular at E. Construct perpendicular. Then you do the radius to the either end where that line touches the circle of inversion. You do that radius to that point and then select that end point. Construct perpendicular. This point of intersection out there, let's pop it right down. That is the inverse of point E, guaranteed. Now from the math we just saw, we should be able to take measurements. The measurements we just did and show that the radius squared is equal to OE times, let's name these points. OG, and I'm giving this a name. So OH squared has to be equal to OE times OG. Well, let's do the measurements and the math. Hang on. All right, so I'm going to select OG as endpoints and measure the distance. All right, so there's a measure for GO, go. Now I got to get OE, because I'm telling you OE and OG are going to multiply to give me the radius squared. So here's that distance. Now I'm going to measure this radius. Measure that length. And now back to the calculator. If it doesn't get snippy with me, let's see if it feels like cooperating. So the radius squared, that's this dude. Let's square that thing. So I got 36.71 for OH squared. And that's going to be 11.86 times 3.09. Really? Really? Let's give it a try. That's almost like 12 times 3. So 36.71 is possible. Let's see if the calculation comes out right. Calculate this distance times this distance. And there it is, the same number that we got before. And I'm going to, of course, drag point E around. And what's going to change? OE is going to change. OG won't change. No, if I drag point E, point G will change too. So OG or GO will change. The top two items here will change. These two dudes will change. But the product, 36.71, doesn't change. So here's an interesting thing. The inverse of a point close to the circle of inversion is close to the circle of inversion. A point and its inverse are near each other. But when I get close to O, look at this. Look how far away G gets from the circle of inversion when E is near O. So this is a big tip for you. When you have to do your own point and its inverse, don't choose a point that's very close to O, because then your work goes off the page that you're working on. Or if you're working on a computer, your work goes off the screen that you're working on. So there it is. This is the big stuff. You've got to be able to do all these things, you know, the stuff that I was talking about here. This is the construction you have to be able to do. You're going to be doing it a lot. It's the construction of a point and its inverse, or given a point, construct its inverse. This construction is going to happen a lot. So get it down. Come and see me sometime in the math department. Maybe we can make a video together. And I'm really liking the wiki. I'm being sarcastic with you guys. I hope you can handle it. But we'll be finishing up the Euclidean stuff in September, and you'll have your first test in end of September, early October. We'll be starting hyperbolic geometry, which, if you know me, my favorite things, non-Euclidean geometry. All right, stay tough, everybody. Talk to you later.